Good day, everyone. Welcome to part 2 of the Physics Latam mini course on supersymmetry, and thank you again for giving us this wonderful lecture, and please take the conference. Thank you.
Thank you very much. Thank you for coming again. So I didn't kill you enough last time for it. Okay, so I will start from what we were discussing last time at the very end of the lecture. Which is basically Coleman-Manzula-Nogo theorem. Remember, just to remind you what we were trying to do, because starting from there, today we will try to overcome the no-go theorem. So remember that basically the Coleman-Manzula-Nogo theorem states that the most general group of symmetries for a relativistic theory is of the form Poincaré. We always require invariance under Poincaré times any possible semi-simple or non-semi-simple internal group. With this equation, I mean that the most general algebra corresponding to the generator of this most general group is made by Poincaré generators plus internal generators, but the internal generators always commute with the Poincaré generators, which are nothing but momentum and angular momentum. Okay, so in particular, let me write things in a kind of sketchy way. This is equivalent to say that if I commute the generators of G with P mu, I will get 0. If I commute the generators of G with M mu nu, I will get 0. So in other words, the generators of the internal group are scalars, Lorentz scalars. Correspondingly, also the parameters of the transformations are Lorentz scalar. Of course, this is equivalent to say that the two Casimir that we picked up in Poincaré, remember, these are P square and the Pauli-Lubansky vector square. They still commute with internal generators. But remember that to P square, we assign the quantum number m square, where m is eventually identified with the mass of the particle, and to W square, with W square, we identify the spin of the particle. Okay, so what we are basically claiming here is that applying any of the internal generators, we will be never able to change the spin of the particle and the mass of the particle. Okay, so this is equivalent to say that the application of G never changes mass and spin. Okay, so said in other words, this is equivalent to say that we cannot apply internal symmetries that map bosons to fermions and vice versa, if you take into account the usual statistic theorems. You know that spin zero, for instance, spin zero particles are bosons, spin 1/2 particles are fermions. So what we are claiming is that we can never mix the bosons and fermions by applying internal generators. Okay, so but the question is, why did people want to generalize this set of symmetries in order to include also the possibility to exchange bosons and fermions? Well, historically speaking, because at that time, we are back to early 70s, people were looking for some grand unification theory, and the the biggest grand unification theory that you can imagine. Of course, eventually you have to be able to accommodate both matter, which are fermions, and interactions, which are bosons. So, having something which, if you have the possibility to accommodate both for bosons and fermions inside a big representation of a very big symmetry group, which may exchange bosons and fermions, then you have realized, of course, a grand unified theory. That was more or less the original motivation. But as I said, so let me write something. So why we like to do that? Because of, original motivation. Was grand unified theories, the attempt to formulate a grand unified theory. Okay, however, as I already mentioned last time, we have an obvious possibility to overcome the Nogov theorem, because the Nogov theorem has one of the assumptions, the fact that, we are talking about ordinary groups, which means the groups generated by ordinary generators, which satisfy a commutation algebra, so they satisfy commutation rules. But as we know from mathematics, we also have supergroups, superalgebras, where generators are also great generators, and some of them satisfy anti-commutation rules, okay? So since Coleman-Dula is based on the assumption that we are dealing with G, which is an ordinary group, the attempt that we can make is to try to avoid this Nogov theorem, generalizing to the possibility that for G to be a supergroup containing also anti-commuting generators. Okay, this is in fact basically the origin of supersymmetry, but instead of discussing this already at the level of the algebra, we will do it later. As promised, now I will spend some time to introduce, let's say, supersymmetry in a hand-waving way. So I want just to show you that I'm able to write down a theory, a very simple theory, which has a sort of, let me call grade group of symmetries. Okay, so now we are going to devote sometimes to this construction. So let me just write it as hand waving construction, because this is certainly I hope it's going to be more intuitive for you. You will see how we really construct by hands supersymmetry generators. Once we have familiarized a little bit with this hand waving construction, that we can move back to the algebra and study supersymmetry for a more rigorous and more general setup. Okay, so what I want to do here is to consider the simplest theory made by, so describing basically the dynamics of one scalar and one Majorana fermion, okay? So consider a theory for one complex scalar plus one Majorana fermion. Let me already indicate the way we call these fields. So phi and phi bar are the two components of the complex scalar. And remember, the Majorana fermion in our convention is written in this way, in a Weyl basis. Okay. Okay, so still to be extremely simple, let's assume that the dynamics of these two particles is free dynamics. So the free Lagrangian has the usual form that you hopefully you know very well. So this is the free, let me even consider massless particles. So the Lagrangian for massless. So it's really the simplest situation, the simplest possible situation. So this is of course the kinetic term for the scalar, plus in ordinary Dirac formulation, you would write the Dirac operator in this way. But then if we move to a Weyl basis, you can rewrite the Lagrangian with our new conventions, where we use even double spinorial indices. Okay, so this is also 1/2 d alpha alpha dot phi, d alpha alpha dot phi bar. Remember, I will remind you a little bit of conventions that we mentioned last time, and this becomes minus I over 2 psi bar alpha dot d alpha alpha dot psi alpha. Okay, just to remind you some of the conventions. We define d alpha alpha dot as sigma mu alpha alpha dot d mu in terms of the usual vector index mu. Sigma mu, remember, are the set of 4 2x2 matrices, which are the identity and the 3 Pauli matrices. I told you already, which is our convention for the spinor. So if you want to start getting some practice with the new conventions, with this double spinorial notation, you can, try to check yourself this equality, how to go from the first line to the second one. Okay, but this is our starting point. Let me first of all mention that, well, starting from this Lagrangian, of course, it's easy to find out the corresponding equations of motion. The equations of motion for the phi field is box phi equal to 0, and of course, box phi bar equal to 0. Nothing surprising. And the equation of motion for the spinor, if you vary respect to psi bar, for instance, you get d alpha alpha dot psi alpha equal to 0. This is the equation of motion for psi, for the left Weyl component. And of course, if you consider complex conjugate, you will get the corresponding equation for psi bar. Okay, so this is something that we will be using later. Now, which are, if you look at this Lagrangian, and I ask you which are the symmetries for this Lagrangian, the ones that we know, I mean, ordinary symmetry is generated by groups. Of course, the way it is written, this is a relativistic theory, so we have invariance under Lorentz, because this is a scalar Lorentz scalar. And it's, of course, invariant under translations. Therefore, we have the usual Poincaré invariance plus an internal symmetry, which is a U1 symmetry, of course, because now we are dealing with complex fields. Okay, so the ordinary symmetries are Poincaré, this is manifestly Poincaré invariant, and a U1, let me call it internal U1 symmetry, which acts on the fields this way. So phi goes to a new field phi prime, which is e to the I alpha phi, alpha constant. And of course, the same thing for phi bar. This will be e to the minus I alpha phi bar, okay? And of course, since phi and phi bar transform with the opposite phase, it's obvious that the phi bar Lagrangian is invariant, okay? Alpha constant. Okay, how the U1 symmetry acts on the fermions? Well, the same. We can have psi going into psi prime, which is equal to I. Here I can have another phase, not necessarily the same as phi, and for psi bar, the same. E to the minus I beta psi bar. Okay. However, I want now to argue and convince you that this Lagrangian has another symmetry, which is no longer generated by, let's say, bosonic generators, but it is generated by a fermionic one. In fact, I can introduce, so there is a third, another symmetry generated by a Majorana spinor parameter that I write as epsilon alpha, epsilon bar alpha dot, given by, so I claim that the Lagrangian is invariant under the following transformation. Delta phi is minus epsilon alpha psi alpha. And of course, if you take the complex conjugate, you will get delta phi bar equal to minus psi bar alpha dot epsilon bar alpha dot. Delta psi alpha equal to minus I d alpha alpha dot phi applied to phi, epsilon bar alpha dot. And let me move it a little bit. And delta psi bar alpha dot equal to 2I epsilon alpha d alpha alpha dot phi bar. Okay, I'm not going to do the calculation. You should do the calculation, okay? Just implement these transformations in the Lagrangian. Of course, as usual, the Lagrangian is invariant when the variation is a total derivative. Because remember that eventually you have to integrate to get the action. So you are free to be left with some total derivative. So when I'm saying that the Lagrangian that I wrote here is invariant under the kind of transformation that I wrote, it means that the variation of L is a total derivative, okay? So you should check exercise, check that under transformations 1, delta L is something like d mu, I don't know. How do I call it? Lambda mu. So it is a total derivative. Okay. Good. So if you believe me, then I'm going to elaborate on this new symmetry. First of all, there is a big difference. We will come back to this point later. And the big difference is the following. Of course, as long as you consider ordinary group symmetry group, you will generate transformations that depend on parameters, like here, alpha, beta, then you will have also parameters associated with the translations and Lorentz booths, which are scalars, which are bosons. bosonic quantities, okay? Alpha and beta are simply ordinary numbers. Whereas here, what I'm claiming is that this new symmetry is associated with the fermionic parameters, spinorial parameters to be correct, because these are bispinors, okay? And they are anti-commuting parameters, because of course, spinors have anti-commuting entries, okay? So epsilon alpha and epsilon bar alpha dot are anti-commuting parameters. Okay, this is already a big difference compared to what we are used to in ordinary symmetry groups. Okay, but let's elaborate a little bit more on it. Okay, so first of all, remember, as usual, that, you know, our main reference to build up, you know, all whatever I can infer from the symmetry of the Lagrangian is the Noether theorem. Noether theorem tells me that whenever you have an invariance of the Lagrangian, you have a corresponding conserved quantity, okay? I expect that even in this case, since I have an invariance of the Lagrangian, I will be able to find out a conserved quantity, okay? So let's see how things work. Okay, let me remind you, so let's consider Noether theorem for ordinary symmetries. Okay, let me just summarize what happens. What happens is that if I have a bunch of fields, let me call this phi generic field, subject to infinitesimal transformations of the form delta phi equal to I alpha A T A phi, where TA are the generator of the symmetry group, okay? Of symmetry group, is that clear? I'm just considering the infinitesimal transformations of alpha much smaller than 1. Okay, then I know that this L invariance and transformation, let me call this 2, implies that we have a conserved current where J mu, this is something that you should know, is the derivative of L with respect to the mu phi times delta phi minus, this is what I called lambda mu. Okay, if the Lagrangian is invariant because it is eventually the total derivative of a local quantity lambda mu, then this is the structure of the conserved current. You can check that this is in fact conserved. Remember, it is conserved on shell if you use the equations of motion for your field. Okay, this is on sorry. This is conserved on shell. Okay, why I'm going through the ordinary case, because what I want to stress here, because it is important for what I'm going to tell you in a moment, is that if you replace delta phi here with the actual transformation that I can read here, and I take into account that I'm applying an infinitesimal transformation, you will agree with me that J mu, the explicit expression of J mu, will turn out to be linear in the parameters alpha A. Do you agree? because the transformation, the phi transformation is linear in alpha A, okay? So this is important. So J mu is linear in alpha A. Therefore, you can always write J mu as alpha A, J mu, let me put J mu A. And in fact, this is the usual statement from Noether theorem, according to which you have a number of conservation laws, because of course at this point you will write that d mu J mu A equal to 0, okay? You have a number of conserved quantities equals to the number of parameters, but the number of parameters at the end of the day equals the number of the group generators. Okay, good. So why I'm telling you that? Because now I want to do, sorry, one more thing. Of course, from this set of conserved quantities, you can at this point write down, well, these are not conserved, I would say conserved current. I can write down a conserved, a corresponding conserved charge. So I can write down something like a QA. What's going on? QA, which is, as you know, the space integral of JA0 component. Okay, and just to close the circle, the QA are the generators of the symmetry. Okay. Of course, everything is bosonic here. We have bosonic parameters here. We have, of course, bosonic generators in the sense that they eventually, not bosonic generators here, that bosonic in the sense that eventually they satisfy a commutation algebra. Okay, let's redo the same thing now using the fact that we have this new symmetry where the parameters are Grassmannian quantities, commuting parameters. Okay, so how did I call this? Okay, in the case for generalizing to transformations 1, of course I can state, because if you just look at the transformations, I can state that the quantity, I mean, the conserved current corresponding to this invariance, if you redo all the procedure from the theorem, will be a current which is linear in epsilon and epsilon bar, because the transformations are linear in epsilon and epsilon bar. Okay, so for simply for analogy, the conserved current will be linear in epsilon alpha, epsilon bar alpha dot. Therefore, we can write that the conserved quantity, the conserved current, J mu, has the following structure. It's like something like epsilon alpha J mu alpha plus epsilon bar alpha dot J, let me call it J bar mu alpha dot. Okay, and of course, the conservation now becomes d mu J mu alpha equal to 0 and d mu J bar mu alpha dot equal to 0. So what is concerned this time is a set of spinorial currents. Okay. This is to say that, you know, I can proceed further. I can, in fact, define spinorial conserved charges that we define this way. So Q alpha will be the space integral of J alpha 0, the time component of the conserved current, and Q bar alpha dot will be the integral of J bar 0 alpha dot. Okay, these are for sure conserved charges. Very good. These conserved charges are what we consider, what we interpret as generators. So these are the generators of transformations 1, in the sense that, you know, for instance, I wrote that delta phi is epsilon alpha psi alpha, remember? This, by definition, for me, is, this I is here for convention, is epsilon alpha Q alpha plus epsilon bar alpha dot Q bar alpha dot applied to phi. This is the way I define the charges, the conserved charges acting on the scalar. The same thing you do for phi bar. That was psi bar alpha dot epsilon bar alpha dot, and this is again epsilon alpha Q alpha plus epsilon bar alpha dot Q bar alpha dot, this time applied to phi bar. And you can imagine you do the same thing. Sorry, I should call this probably with another index. Psi beta, you apply to psi beta, and the same for psi bar beta dot, applying the supercharges to psi bar beta dot. Okay. At this point, given that we have the transformations 1 explicit in this equation here, I can infer from these explicit transformations how Q and Q bar, the supercharges, act on the single fields. In fact, well, this is easy for you to see already from here. You see, if this commutator has to give rise to epsilon alpha psi alpha, on the left-hand side, I do not have any epsilon bar term. It means that here, Q bar alpha dot, when acting on phi, has to be 0. Whereas Q alpha, when acting on phi, has to be exactly psi alpha, up to the I. Is that clear? Okay, so comparing.
Sorry, can I ask a question?
Sure.
Are you writing a commutator of the charges with phi?
Yes, I'm writing commutators. Yes, these are still commutators. I will show you in a moment, because these are scalars. They are not spinorial quantities. For the time being, this is a commutator, but let's see what happens. Is that your question?
Yes. Okay, we are seeing them as operators, both the field and the charges.
These are operators acting on phi. Yeah, I interpret the charges as operators acting on phi.
Okay, thank you.
Okay. And the operator is basically the commutator of the charge with the field. So what I define, if I compare with transformations 1, is the following. So comparing, no. With the transformations 1, we find the way this Q and Q bar act on the fields. In fact, as I already mentioned, from the first line, it's easy to see that Q alpha applied to phi has to be probably I psi alpha. Okay, whereas Q bar alpha dot applied to phi has to be 0, because we do not have any epsilon bar here. Okay, if we do the same on phi bar, it will be, of course, the opposite. We will have that Q alpha phi bar is equal to 0, whereas Q bar alpha dot phi bar, this is equal to I psi bar alpha dot. Okay, now pay attention to the transformation of spinors. Let me do it more carefully. So for spinors, first of all, I have to find out how to compute this object. These are all anti-commuting quantities, both epsilon q and also psi, of course. Therefore, it's an easy game to play. You know, how, in order to find out how q and q bar acts on psi, you have to bring epsilon and epsilon bar outside the commutator, but this will give you eventually an anti-commutator. This is the right thing that you should write. I hope you agree. Therefore, if you compare with 1, comparing with transformations 1, you will find that Q alpha applied to psi beta is equal to 0, whereas Q bar alpha dot applied to psi beta, but this time the application is through anti-commutators. Okay, this is to d beta alpha dot phi. And similarly, you will have Q alpha psi bar beta dot anti-commutator, which is minus 2d alpha beta dot phi bar. And Q bar alpha dot psi bar beta dot equal to 0. Okay, therefore we managed to, you know, define sort of a formal charges, formal operators, Q and Q bar, which I know how they should act on the fields, on you know, on the scalar phi and the spinor side. Okay, so this is not, of course, the end of the story, because at this point, let me call this 2, and this is, both of them are 3, because basically, now that we know how the supercharge, let me call already them supercharges, are how Q and Q bar act on the fields, so which is the explicit realization of these supercharges on the fields of my theory, I can see whether the algebra closes. What does it mean? Basically, whether the algebra satisfies, first of all, using Jacobi identity, satisfies a set of commutation and anti-commutation relations which close on this, on the self, okay? In the sense that, for instance, if I start applying twice Q or twice Q and Q bar to a field, I want to see if what I get on the right-hand side is still some generator which is inside my set of symmetry generators, or I do generate, I do give rise to new generators. For the time being, you see, I'm pretty happy because the way we wrote the transformations leads necessarily to the fact that when I act with Q and Q bar on the fields, at most, I have here some derivative operator, but the derivative operator is one of our friends, because this is one of the, this is basically the momentum. If you move to momentum space, the derivative is the momentum, so it's the generator of translations. Okay, so what I should do now, but this is kind of I can tell you how to do it. You will do it because otherwise we will spend the rest of the lecture just doing trivial calculations. Let me first of all tell you what I want to do, then how you should do it and what is the result. Okay. So what I want to do is now to see what happens if I start anti-commuting the generators, the QQ bar generators between themselves. So this can be, let me see, let's construct the QQ bar algebra. It means that what I want to do is to consider, for instance, the anti-commutator of Q alpha and Q beta. Remember that alpha and beta takes value 1 and 2. So what I am dealing with are two Q generators, Q1 and Q2, and two Q bar generators, Q1 dot, Q bar 1 dot, and Q bar 2 dot. Okay, so in total, for the time being, I have 4 generators. Okay, so I am certainly free to see what happens if I start anti-commuting Q alpha with Q beta. Okay, how do I do that? Well, I try to apply QQ to phi and see what happens here. And of course, the same thing has to happen when I apply QQ, so the anti-commutator, to the spinors. I expect to find on the right-hand side is everything is meaningful. I expect to find on the right-hand side some operator acting on phi here and some operator, the same operator, acting on psi gamma here. Okay, good. So the only thing that we know is the action of Q on phi and Q on psi. But this is something that I can exploit. Why? Because I can rewrite the left-hand side here using Jacobi identities, okay? But you have to use grade Jacobi identities because these are anti-commuting objects. Okay, so I hope you know where to find the usual anti-commuting Jacobi identities. So using grade Jacobi identities, what you will do will be to trade these commutators. Let's take, for instance, the one acting on the scalar. You can trade with the commutator with something up to signs, which now are of the form phi Q alpha. Remember that you have to cycle the entries of the commutator, this with Q beta, and this will be plus or minus. You have to look at the Jacobi identities carefully. And this will be again something like Q beta phi Q alpha. Okay, this is the first thing that you have to do. Of course, then you will do the calculation for psi. But at this point, you know these two commutators because we wrote already that these two commutators are nothing but I psi alpha and plus or minus. This is this is minus and this is plus I psi beta. Okay, but again, you know at this point the explicit expression for Q acting on psi. So you're done. Okay, so if you complete the calculation, okay, you will find that Q alpha anti-commutator with Q beta applied to phi This is equal to 0. If you compute the same with Q bar, again, you will get 0. But if you compute Q alpha, Q bar alpha dot applied to phi with the whole procedure, you will end up with 2I d alpha alpha dot phi, which is beautiful. This is what I was expecting, in fact, because what I get, first of all, is that the right-hand side is once again back to be expressed in terms of phi, and it is one of our well-known operators. This is translation. This is a derivative acting on phi, okay? I hope to find, so forget about the first two are trivial. I hope to find the same expression when QQ bar acts on the spinor, on psi, okay? Here, there is a trick that I have to mention. Well, it's not really a trick, it's a subtlety that I have to mention, which is the following. Okay, now redo the same for spinors. In particular, what I want to compute is the anti-commutator Q alpha, Q bar alpha dot applied to psi beta. Okay, if you use again Jacobi, the great Jacobi identities, blah, 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 you use the explicit transformations that we introduced in equation 1, you will end up, unfortunately, with the following expression. This is beta, sorry. E beta alpha dot psi alpha. Okay, why unfortunately? Because I would like to have, of course, the operator applied to the same field. So I would like to have an operator on the right-hand side applied to psi beta, not psi alpha. Okay, so this is sort of little problem, but how can I proceed? Of course, what I can do is to add and subtract what I would like to obtain. So if I add and subtract 2I d alpha alpha dot psi beta, the expression doesn't change, but what I can write is 2I d alpha alpha dot psi beta, which is what I would like to get, plus 2I, and here I'm left with d beta alpha dot psi alpha minus d alpha alpha dot psi beta. Okay, well, this is a very nice expression because this is anti-symmetric in alpha beta. Okay, I remind you that last time when I was going through the conventions, I told you that there is sort of fierce identity for this kind of anti-symmetric expressions. So this is eventually given by what I would like to obtain plus 2I if I use Fierz identity. Fierz. This is epsilon beta alpha d gamma alpha dot psi gamma. Okay, just check the equation that we wrote, the identity that we wrote last time. Fine, so what is the conclusion? What do I recognize here? This is nothing but the equations of motion for the fermion. Okay, so this is equal to 0 on shell. Okay, so what I find is that the anti-commutator of QQ bar acting on the spinor gives me the correct result, the expected result, at least the same result that I obtain for the scalar, only if I remove this last term, which is nothing but the equations of motion for spinors. So this is, I mean, we can reformulate in a more elegant way this statement. Basically, the statement is that the algebra closes on shell using the equations of motion for spinors. Okay. In fact, at this point, okay, you should redo things also for the bar quantities. You can enjoy doing it. Compute Q alpha, Q bar alpha dot also on acting on phi bar and psi bar alpha dot, and eventually we find the following algebra. When my, let's say, my supercharges act on the fields of my theory, this is what happens. QQ and Q bar is equal to 0, which means that Q, in fact, simply means that Q and Q bar are Grassmannian quantities. It means that, for instance, Q1 squared is equal to 0, right? Q2 squared is equal to 0. Okay, so let me maybe say something. So from here, this is equivalent to say that Q1 squared is equal to Q2 squared equal to 0. Q bar 1 dot square is equal to Q bar 2 dot square equal to 0. Okay, so they are Grassmannian quantities, they anti-commute, whereas we have a non-trivial algebra given by this anti-commutator. Okay. This is not the end of the story, because remember that I have to merge everything inside Poincaré. This everything has to be consistent with Poincaré invariance, which is, and so in order to complete the picture, I also have to investigate which are the correct commutation rules of QQ bar with the generators of the Poincaré, which means with P mu and N mu nu. Okay. So putting together with the Poincaré generators, we argue that when we commute Q with P mu, we get 0, and the same for Q bar alpha dot. Why? Because basically Q and Q bar are translational invariant. Okay. However, when I commute Q alpha with the generators of Lorentz transformations, which means when I act with the Lorentz transformation on Q, of course, I will get here something non-trivial, because Q alpha, after all, is a spinor. It brings a Weyl index alpha. Okay, therefore, it transforms as a Weyl spinor under Lorentz. And in fact, what you find is that this is equal to minus plus depends on the conventions, sigma mu nu alpha beta Q beta. I will tell you in a moment what sigma mu nu are, and mu nu Q bar alpha dot is equal to minus 1/2 sigma mu nu bar alpha dot beta dot Q bar beta dot, but I should put here alpha dot up. Okay, since Q alpha, Q bar alpha dot are Weyl spinors. Okay, and sigma mu nu and sigma bar mu nu are what you inherit from gamma mu nu. Remember, on spinors in the standard formulation, standard notation, On spinor, we act with gamma mu nu, which is the commutator gamma nu. If you move to this other, let's say, basis, by basis, what you will find is that sigma, everything is expressed in terms of sigma mu nu, which is by definition I over 2 sigma mu alpha alpha dot sigma bar nu alpha dot beta minus sigma nu alpha alpha dot sigma bar nu alpha dot beta. Okay. And similarly, sigma bar nu alpha dot beta dot, well, we will have, of course, the same thing, but with sigma exchange with sigma bar. So this is alpha dot alpha, sigma nu alpha dot, sorry. This is alpha. This is alpha. This is sigma alpha beta dot minus sigma bar nu alpha dot alpha sigma nu alpha beta dot. Okay, so if I put together this set of algebra commutators, probably let me call it 4, with this, no, let me put everything, with this set of anti-commutators, no problem, this is 4 and the other one is 5. Okay, the set of commutators 4 and 5, where now you can identify this with 2p alpha alpha dot, which is proportional to p mu. You see, the algebra closes because when you commute or anti-commute two generators, you produce generators of the same set. So when you do anti-commute QQ bar, you produce P mu. And here, when you apply non-trivially the Lorentz transformations, you do produce something which is still proportional to the generators of the algebra, okay? However, remember that in order to get this result, we had to use the equations of motion for the fermions, okay? So what I have written down at this point, so summary, sorry. Four plus 5 is what we call the on-shell SUSY algebra. On shell because, you know, I have to use the equations of motion in order to close the algebra. Let me go through the last point concerning the possibility to define the algebra off shell. This is just a simple observation, then we will make a little break. Okay. Of course, we are not completely happy to live with an algebra which closes only on shell. So we want to go off shell to move off shell. Okay, how do we do it? Well, you might think that this comes just out of the blue. Yes, at this level, yes. It's something that I just tell you, and then you have to check that this works indeed. In order to go off shell, what I'm doing here, in order to go off shell, we introduce another degrees of freedom, another complex scalar, let me call it F and F bar. And you generalize your theory to include also this scalar. So we generalize the Lagrangian. Of course, we still have the original free terms for the scalar and the fermion. Yeah. And now you add numbers are always conventions, of course. So don't worry. I mean, I put 1/4 here for convenience, but you can put whatever. The important thing is that the extra term that you add for this new complex scalar is just an algebraic term. It doesn't contain any derivative. In particular, it does not contain any time derivative. Therefore, F is just a kinematic degrees of freedom. It does not propagate. Okay. Okay. So note that F does not propagate. Okay, together with this generalization of the Lagrangian, we have also to generalize the SUSY transformations of the fields to include also F, of course. At this point, we generalize the transformations as we do here. Okay, so we do not change anything. Let me check if I did something correct. Wait a second. No, I have just a sign. Let me check because I don't remember that I had a sign. Probably I forgot about it. Yeah, here I have a sign. In fact, it should be minus and this should be minus. Otherwise, you may compromise the transformations. And in fact, here we had a sign correct. The correct sign is the one that I wrote to begin with in 1. Okay, sorry about that. I forgot the sign there in the intermediate step. Okay, so let's go on. So we generalize the transformations, let's say 1, as follows. Okay, so we do not change the phi transformation. This is still the same. Therefore, we do not change the phi bar transformation. Rather, we are going to change the psi transformation. This is what we had already. This is phi epsilon bar alpha dot by adding this extra term proportional to F, and the same thing for psi bar. Of course, this comes by taking the complex conjugate minus epsilon bar alpha dot F bar. But at this point, I have to infer also the transformations for F and F bar, of course, because now we have extra terms. Delta F is equal to minus 2I epsilon bar alpha dot d alpha alpha dot psi alpha, and delta F bar equal to minus 2I epsilon alpha d alpha alpha dot psi bar alpha dot. Okay, this is kind of, I would say, intuitive procedure, at least if you look at the transformation for F bar, because the transformations for F bar are proportional to the equations of motion of spinors. So if I were to set the spinors on shell, this right-hand side would be 0, okay? And I could get rid of F bar, as we did earlier. But now I don't want to put the fermions, the spinors on shell. That's why, let's say, the price I have to pay is that I have to deal with these extra degrees of freedom. Good, what I'm claiming, and you should check that. So this is another exercise. These are transformations 6. Prove that or show that L, this new L, let me call this L tilde, because now we include also the F and F bar degrees of freedom, show that L tilde is invariant under transformations 6. Okay. This is, let's say, point 1 of the exercise. Point 2 show that using transformations 6, the algebra of Q and Q bar acting on a spinor psi beta gives the correct expected result without using the equations of motion for psi. Okay, therefore, algebra generated by transformations 6 closes off shell. I don't have to use equations of motion for any of the fields. Okay, at this point, the correct statement is that, you know, the set of generators which give rise to this transformation 6, not the original 1, plus the usual commutators with the Poincaré generators provides an algebra which consistency closes off shell, and this is what we will call supersymmetry algebra. Okay. Okay, maybe this is the right time to have a break. Okay, so let's keep discussing this point. In particular, yeah, let me write something that was asked before the break. Well, first of all, okay, if you manage to check this second point, this would be very useful because you really appreciate the role of this auxiliary field, why we like to include auxiliaries in the construction. So as I said in words, let me also write something. F bar are non-dynamical fields. Okay, this is first thing. Their equations of motion are F equal to 0, F bar equal to 0, as you can infer from the Lagrangian. Consistency of transformations 6 for psi and psi, sorry, for F bar. Consistency means with the equations of motion. Consistency means that if we use the equations of motion and we set F bar equal to 0, then of course this has to be consistent with delta F equal to 0 and delta F bar equal to 0, right? But if I go back and look at the transformations for F and F bar, as I was saying, the transformations are proportional to the equations of motion for the spinors. So this is equivalent to say that spinors go on shell. This is everything is perfectly consistent. In fact, you can decide whether you want to avoid the use of auxiliaries, but then, as we read from this set of implications, you will have to set the spinors on shell in order to close your algebra. Otherwise, if you keep F and F bar inside your set of degrees of freedom, though they are just auxiliary, not propagating, then you can relax the condition of the spinors, and the spinors don't have to be set on shell. Okay, so this is really a question of, you know, what is better for you to do according to which is the physical problem that you are investigating. Okay, beyond that, now that we have constructed basically a super algebra, because as I said, you know, if you put together the set of transformations, sorry, I have to go, that I read here, sorry, no set of transformations, set of anti-commutation rules that I read here, together with the ones which involve the generators of Poincaré, what I can claim, as I said, is that 4 plus 5, so the set of identities 4 and 5, give me an algebra, which is a great algebra. It contains generators which satisfy commutation rules and generators which satisfy anti-commutation rules. Okay, so this is what we call a great algebra. Okay, and this is what we call n=1 supersymmetry algebra. So let me say conclusion. 4 plus 5 is a great algebra. It is what we call n=1 supersymmetry algebra. That's supersymmetry. Okay, and we will analyze it in detail, but for the time being, let's just stick to what we have done by hands, basically, because we can already make a couple of interesting observations that we can grasp from the algebra. The first observation is that, you know, when we write transformations, for instance, like this one, what we are doing is transforming a boson into a fermion. As usual, we have to use the spin statistic theorem, you know, scalars are bosons and spinors are fermions, okay, which can be formulated in a more appropriate way. It means that we have a bosonic state, which is obtained by acting with your boson, with your scalar phi on the vacuum. This is a bosonic state. If we have a fermionic state, which is obtained by acting with the spinor psi on the vacuum, then what we have found is that if we apply a supersymmetry charge to a bosonic state, we end up with a fermionic state, okay? And similarly, if we apply Q to a fermionic state, we get a bosonic state. Let me call it BT, that's not the same one. Okay, so we really managed to transform bosons into fermions. Okay, the second observation, just an intuitive observation, is the following. If you look at the algebra 4 and 5, you will immediately realize, so from the algebra 4 and 5, we obtain that if you commute any of the, when I write Q, I mean also Q bar, of course. when I commute any of the supersymmetry charges with the p square, remember the famous Casimir, this is still 0 because p mu q is 0, okay? Therefore, p square is still a Casimir of the n equal 1 SUSY algebra. Okay. Said in other words, it means that when you act on a state with some q, as we were doing here, when you act on a state with some q or q bar, and the state corresponds to a particle of a given mass m, you will never change the mass of the corresponding particle, fermionic particle. So it means that the bosonic particle and the fermionic particle, which are related by the action of q or q bar, they have the same mass. Correct? Okay. So from here, I can say that B and the fermionic state obtained by the action of some Q acting on B have the same mass. Okay. However, if I now commute Q alpha with W squared, remember the other Casimir of the Poincaré algebra, this time, since Q is a spinor and Lorentz transformations act on spinors in an untrivial way, you immediately get convinced that in this case, this is not longer 0, okay? Therefore, W squared is no longer a Casimir of the n equal 1 SUSY algebra. In other words, it means that when you act on a state, on a particle with Q and Q bar, you will change the spin of this particle. Of course, if I have to survive with the spin statistics theorem, this is what I already read here. Okay, so therefore, acting with Q or Q bar, we change the spin of the particle. Okay, I'm just saying, in other words, what I have said already here. You know, when I say that if I act on a bosonic state with Q, I get a fermionic state, this is the same thing that I'm now recalling here. Okay, therefore, particles can be arranged into SUSY, what we call multiplets, which have nothing but representations. We will come back to this point later in one of the next, in the next lectures. This is nothing but the representations of n equal 1 algebra. Okay, and these multiplets will be, let's say, all the particles in a given multiplet have the same mass, because I cannot change the mass of the particle by acting with Q and Q bar, okay? But they will have different spin. Don't worry if you do not understand completely what I'm telling you now, because we will construct explicitly SUSY representations and multiplets in a very detailed way. So we will come back to this point. This was only to mention that if I stick to physical degrees of freedom, intuitively, you can imagine that at this point, if supersymmetry is a symmetry realized in nature, it means that whenever I have a bosonic particle, I also have the corresponding superpartners, which will be a fermion, and vice versa. Whenever I have a fermionic particle, I will also have to observe the corresponding bosonic superpartner. Okay, in particular, at the level of, let's say, physical particles, I expect if supersymmetry is not broken at a given energy scale, we should observe a doubling of particles, because, for instance, let's consider first of all matter particles. So let's say quarks and leptons. I don't know, let's take for instance the electron. You should observe also these are fermions, of course, the bosonic superpartner. That we will call squark, selectron, and so on. Okay, if we consider interactions, so gauge fields, A nu A, these are of course bosonic. I mean, the interactions are mediated by bosonic mediators, bosonic particles. We will have to observe also the corresponding fermionic superpartner, which is typically called the gaugino. Okay. If we have, for instance, the graviton, let's keep it separated from the rest. The graviton will have a corresponding fermionic superpartner, which is called gravitino, and so on and so forth. Okay. Of course, we do not observe this kind of particles. Yes. Please.
The fields like the gaugino will be again necessarily interactions.
Yes, of course. Yeah.
So, okay, in that case, we would have a fermionic
yeah,
field.
you have to you have to supersymmetrize the gauge covariance of your theory. Yeah.
Okay, thanks.
Yeah, you have to do, but we will do it. Okay. Good. So this is sort of you know, intuitive idea on how I can introduce spinorial generators in a theory, therefore generate sort of supersymmetry, what we call supersymmetry. Okay, supersymmetry, as you heard probably already, requires that to each particle you have a corresponding superpartner, blah, 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 the usual story. But before, you know, moving to a more rigorous study of the algebra and all the physical properties that we can grasp from the algebra, before constructing explicitly supersymmetry theories, blah, 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 I need still to tell you why we are so fond of supersymmetry. Okay, because of course, supersymmetry is definitely broken. If supersymmetry exists, it is definitely broken at the energy scales that we can reach in accelerators. Because of course, we have never observed this doubling of the particle spectrum, okay? It may be that the supersymmetry exists at very high energy that are totally unreachable with the current kind of experiments that we have managed to do. It could be that supersymmetry is present at the Planck scale. But in any case, there must be some supersymmetry breaking mechanism in such a way that, you know, in nowadays we do not observe super partners for our particles. Okay, so the question is, though there is no evidence, you know, experimental evidence about supersymmetry, why we are so fond of supersymmetry? So why we really want supersymmetry? Okay, there are still some, I would say, more historical reasons, which are still valid. They are good arguments, but there are also more modern motivations. Okay, so let me go through this big set of motivations. I hope, yeah, we should go a little bit faster. Okay, so first of all, the typical historical motivations that you can find in any introduction of any book, any review on supersymmetry are the following. Well, first of all, if you have supersymmetry, as I said, to each bosonic particle should correspond, you know, if superpartner, fermionic superpartner should correspond and vice versa. On the other hand, in quantum field theory, we know that if you have virtual particles flowing inside loops, so you are really considering quantum corrections to physical observables, usually bosonic and fermionic fields inside the loop, let's say bosonic loops and fermionic loops appear with a different sign, with an opposite sign. This somehow ensure sort of nice cancellation, at least partial cancellation of ultraviolet divergences. And what happens is that while in a bosonic non-supersymmetric theory, you may have very severe ultraviolet divergences, for instance, quadratic divergences. In supersymmetric theories, you can have at most logarithmic divergences, which are definitely milder. Okay, so let me write something. So in quantum calculations, fermionic loops have opposite sign compared to bosonic ones. Therefore, having virtual particles plus their superpartners might ultraviolet divergences. Okay, and a very important example is, you know, the famous hierarchy problem. You know that if in the standard, let me say example, in standard model, if we compute one loop corrections to the Higgs mass, we find that at one loop, you have to introduce a scale, introduce a cutoff, non-trivial cutoff, lambda. What you find is that the first correction to the X max is given by this diagram, where you have quarks inside virtual quarks. Okay, and typically this gives rise to a correction to the X mass, which is proportional to lambda square. So this is what we call the quadratic divergence. Okay, but if you move your cutoff quite high in energy, of course, you risk to obtain a situation where the one loop correction to the Higgs mass is bigger and even much bigger than the original value of the Higgs mass, which is something that doesn't make any sense. Therefore, either you do sort of fine-tuning as our phenomenologist colleagues do, or you assume that there might be, together with the virtual quark running around the loop also, so in order to mild the quadratic divergence, we consider loops with new scalar degrees of freedom, which are nothing but the superpartners of what we call the quarks. Okay, and one can show that when you can find the calculation done explicitly, for instance, in the book of Turning. Well, if you do the calculation and you find that if you insert, if you add these extra contributions due to scalars, and this extra contribution, let me write this way, these are the scalars, this quark, and they have both kind of contributions. If you set the parameters, in a very specific way, you may find that, these are also, this is quadratic divergent, this is log divergent. Okay. But if you fit the parameters appropriately, you can find that this quadratic divergence cancels this quadratic divergence, and you are eventually left with just logarithmic divergences. Okay, and this is very, very important. And at that time, physicists were led to think that, okay, maybe with supersymmetry we can make all the theories finite, or at least renormalizable with a very nice renormalization properties, blah, blah, blah. This is in particular because of these nice cancellations of ultraviolet divergences, people started thinking that maybe if you apply supersymmetry to gravity, you can cure the severe problems related to the non-renormalizability of gravity. So people start thinking that maybe supergravity is renormalizable, okay, at that time. Supergravity, which means gravity plus supersymmetry, is renormalizable. Unfortunately, not. The only thing that you obtain is that, of course, the situation improves a lot, and, kind of pathologies that in ordinary gravity can be found already at 1, 2, 3 loops, lower orders, are pushed towards higher orders, but sooner or later you will find pathologies, okay? Except maybe, but this is still an open question, that maybe for n equal to 8 extended supergravity, people start doubting that this theory might be finite, but we have no yet the final answer on this point. Okay, but anyhow, this is more or less a kind of physical motivation why people start loving supersymmetry. Another motivation that you can find in basically any book is the grand unification theory. So if we believe in grand unification theory for the standard model, what you can find is that if you extrapolate the behavior of the three coupling constants of the standard model, strong, weak, and electromagnetic, towards high energies, if we do not have SUSY, you will find a behavior like that. So if here you put this energy scale, this is the behavior of the coupling constant. You find that for SU3, you will get something like that. For SU2, you will get something like that. And for U1, you will get something like that. But, you know, the unification is not very nice. However, with SUSY, this plot improves a lot because what you get is that basically the three coupling constant seem to meet indeed more or less in a single point, which is about 10 to 16 GeV. So this is another way, another argument to believe to supersymmetry. Okay. However, we do have many more modern reasons why we should keep supersymmetry in our game. These are, I would say, more mathematical reasons, conceptual reasons. Let me put modern. What are modern reasons? Why we love supersymmetry. Okay. Okay, first of all, we know that if we believe in string theory as a very powerful mathematical framework where we can try many things, including quantizing gravity, we know that string theory is consistent only if we have supersymmetry. Okay, so string theory requires supersymmetry. Let's say, let me call it a spin-off of string theory is ADS CFT. Of course, at the end of the day, we would like to formulate the correspondence for non-supersymmetric and non-conformal theories. But for the time being, you know, we know that the ADS CFT works in a beautiful way if we have super conformal theories. Okay. So it's not that it requires, but works well with supersymmetry. There are many other reasons related to say dualities, these kind of things, but I learned that there will be some future lectures about duality and supersymmetry. Let me mention another reason. This is really a mathematical but very powerful reason to study supersymmetry theories, which is the following. If the theory, let's say quantum field theory has enough, and enough one should be more precise. What is the meaning of enough? Supersymmetry. Okay, but for the time being, just keep it as enough. If we have enough supersymmetry, okay, then we can solve this theory. What is the meaning of solving the theory? Solving the theory means that we manage to compute the effective action or the partition function, whatever is the object you are interested in, exactly, okay? Which means solve, compute the effective action exactly, not perturbatively, not strong coupling, not on the lattice, exactly, using what we call supersymmetry localization. Which is based on a very simple observation due to Witten back in the past, but later people start considering it in a more serious way. So I can tell you, yes, I think we have the right time up to the end to just to go through very quickly the idea of supersymmetry localization, because this should somehow convince you that having supersymmetry and exploit supersymmetry for doing these kind of things is very convenient. Okay, so suppose that I want to compute, the effective action of the generating functional for my theory. So this is defined as the functional integral on a set of fields. Let me call them collectively phi, e to the minus s. Let me take a Euclidean signature. Okay, if you manage to compute this object exactly, you have solved the theory. Okay, typically we do not, if the theory is interacting, of course, I assume that S is an interacting action. If the theory is non-trivial interacting, typically we don't know how to compute exactly this object. And typically what we do is to apply perturbative methods, or if we are a strong coupling, we try to put the theory on the lattice, these kind of things. Okay, but I can show you that if I have supersymmetry, I can compute this object exactly, as I said, using localization. Okay, so suppose the theory allows for an invariance under the action of a SUSY charge Q, just Q, one charge Q, okay? And for simplicity, but this is not necessary, just for simplicity, we assume Q squared equal to 0, okay? It could be Q squared equal to some bosonic generator, but let's take Q squared equal to 0. Okay, at this point, since Q acting on the action is equal to 0, okay, we can deform W in the following way. So W will now depend on a number. T is just a positive real number. And this is by definition given by the usual functional integral, e to the minus s of phi. And here I deform my action, adding a term like this. This is T times the action of Q on the integral of some local quantity. Okay, sorry. First of all, this is for sure Q invariant term, because since Q squared is equal to 0. So if I act with another Q, I will get Q squared acting on something, but Q squared equal to 0. So this is Q invariant. Therefore, the addition of this extra term does not spoil supersymmetry in my theory, okay? Fantastic. Now, what happens if I take the derivative of W respect to T? Okay, what happens is that I will bring down this term, Q integral of V. And then I'm still left with e to the minus s plus t q, the integral of v. Okay, but since everything is q invariant, I can rewrite this as the integral e to the minus s of q, the integral of v, e to the t, the integral, the anticommutator of q, the integral of v. Okay, because q acting on this part is just trivial. Very good, but by definition, let me call this quantity A. Okay, by definition of functional integral, this is the expectation value on my interacting vacuum of what? Of this operator QA. Okay, which is QA plus AQ 0. But if the theory is supersymmetric and at the quantum level supersymmetry is not broken, something that we can reasonably assume, if SUSY is not broken at quantum level, then when you act on the vacuum with Q, this is equal to 0. The vacuum has to be supersymmetric. Has to be SUSY invariant, okay? Great. Therefore, this is equal to 0. Okay, so what I found is that, first of all, I deformed the action adding this extra term. And now what I find is that in any case, my, let's call deform generator does not depend on T, because the derivative with respect to T is equal to 0, okay? Okay, so since the derivative of W is equal to 0, it means that W of T does not depend on T. Therefore, what you can write is that W of T is equal to W of 0, which is your original object that you have to compute. But this is also equal to W of T equal to plus infinity, not going limit for T approaching plus infinity, T equal to plus infinity. Okay, because W does not depend on T. Great. So according to this chain of identities, I can compute, I can trade the evaluation of my original W with the evaluation of this object. Okay, if I send T to, let me say, if I set T equal to plus infinity, at this point, if I'm go back to the definition of W of T here, what I find is that, it's like doing semi-classical approximation, but this time semi-classical approximation is no longer an approximation, is exact. However, I can apply the usual semi-classical methods, okay? And for T going to infinity, the only non-trivial contributions to these functional integrals are the configurational fields which make this anti-commutator vanishing. Okay, this has to be 0. Okay, therefore, we compute W of t equal to plus infinity using semi-classical approach. Okay, therefore, the only non-trivial contributions to the integral, to the functional integral, are configurations, are field configurations, solutions of Q, the integral of V equal to 0. Whatever is V, of course, what you obtain here is a set of, you know, in general configurations, discrete configurations. If we deal with the gauge theories, this will be in general set of matrices, and therefore what you manage to do is to trade your original functional integral with an integral that, thanks to the limit and thanks to the semi-classical approximation, boils down to an integral over a set of matrices M e to some function of M. But this is no longer a functional integral. This is an ordinary integral. It is a matrix integral, but it is an ordinary integral. And in general, we know how to compute ordinary integrals, even if they are matrix integrals, okay? Okay, and for many supersymmetric theories in 4 dimensions, in 3 dimensions, in 2 dimensions, there are millions of examples where you can really compute this the functional integral as an ordinary integral. If you are interested in understanding a little bit more about this, the application of the localization to different supersymmetric theories, not now, not before ending my course, but afterwards, when you know already many things about supersymmetric theory, supersymmetric quantum field theory, then you can have a look to PhD thesis by Peston. He did a beautiful job about applying localization to many supersymmetric theories. Okay, so I think for what is my taste in this, in the last few years, I think this is one of the most powerful reasons why I keep studying supersymmetry. Because, you know, then you can do a lot of things. Okay, I think it's time to stop for today.